details. If you see steel profiles, the web thickness is designed to not buckle for shear, okay, but it's very, very thin. Most of the movement is carried by the flanges, right? Top flange and bottom flange. Therefore, you will have very thick flanges for steel sections. And this outstand is also based on local buckling of the flanges. That's how those shapes are designed. Even in Indian standards, the standard shapes you have, they're all designed based on web buckling under shear and preventing flange buckling during flexure. That's the way they are designed. But if you see this section, the thickness here is same as this thickness here and this thickness here. There's a reason for that, because they are very weak in buckling. So they have made this stockier, thicker, made the web thicker. So you will see if you apply steel code to design of this, it will not work. There is, if you have interest, I can send you a reference to the European standard. They have a European standard for pultruded section. Not many people are using it, but it's available. In American standards, we don't have anything for pultruded sections. There are a lot of publications, like people have done research and they publish, say, these are recommended guidelines for design. But those are not standards. For an average, for day-to-day application, you need a standard. That way you don't have to go and look for all the research publications and then use your judgment to apply or not apply those design equations. Does it make sense? Because you don't want that responsibility. You don't want to take responsibility in terms of someone else's research. Whereas if I have a guideline which is a standard, I'm not taking any responsibility. I'm just using this, right? There is a difference. Do you see the difference? So that's the reason you need standards, to protect you from liability. If something fails, then you can at least say my basis is this. I use my engineering judgment and this is what I get. Okay? Right. Any other question? Okay, and there are more of these. Actually, they even have, like if I don't tell you this is FRP material, you will not even know that these nuts are FRP nuts. These are not metal. So they have anchor boards and nuts, everything in FRP. Okay, so this is what I was talking about. This Indian company is actually flooding the market with this type of grating, industrial grating. And it's working well. People are buying it. That means it's working. So you can make specialty sections like this. So these are plates glued onto other plates to make FRP built-up section. This was used in a bridge. And then when you are, of course, these are all demonstration projects. You really you have to be careful when you want to implement this in your own project. So once again, with these kind of sections, if I don't tell you this is a FRP frame, you will not be able to tell that, right? It looks exactly like your steel frame. And buildings, same thing here. You have these beams, FRP beams. Once again, you cannot tell the difference between steel beams and FRP beams. Okay. Do you see anything different here? I'm sorry? I can't hear you. Do you see anything interesting in this? Say that again. I think some of you said the right thing, but I want to hear it more loud. It's very lightweight. You can see this is a front end loader. It's just for excavation, right? That's a very front-end loader. Almost every big contractor will have this equipment, right? So you are able to pick up this panel with a front-end loader. It's very, very light, very light. Big advantage. And see how many you have on this standard truck. You can have 1, 2, 3, 4, 5, 6. 6 that I can count off. I don't know. Maybe they have more. But it makes a big difference in terms of cost, because the transportation of all these heavy, precast elements can be very expensive. So you see these ones, they are just straps. They are not even chains. So that's the advantage of FRP. You know what I mean? Yes. Can you speak loud?
By utilizing this FRP composites, self-weight reduction is the major
Biggest advantage. Yes, absolutely.
But in earth-draining structures and dams, self-weight is the major key role.
Right, I know.
Key part.
Yeah.
Then how we utilize that FRP composites in dams and retaining walls?
Maybe that's not a suitable application. Or you place FRP liners on the front, waterfront. That's what I would do, because for gravity dams you definitely need you need concrete or something heavy. Yeah, I agree. Okay. So sometimes weight is such a big deal. I'll tell you why. Let's say you are designing a bridge and you are using composite or FRP deck. You make it so light, right? So the columns and even the beam, everything becomes lighter because of that. And your foundations, right? That's a big deal too. If your soil is weak and you want to design a bridge on a weak soil, instead of going all the way to the rock, if it is there, if you have to use some kind of piles or something like that. Instead of that, you can probably get away with spread footing, I don't know, depending on your design. If you are able to reduce the self-weight of the deck is the biggest contributor to weight, right? So that's a big advantage. Same thing here. In this bridge also, you can see they put together this bridge, maybe 100 feet, about 30 meters or something like that, in less than a day. You can put them all together, everything. So you can start allowing traffic in less than 2 days. That's a very big advantage, because if you are rerouting or you are closing the road for, let's say, 6 months, that's a big problem. At least it's not acceptable in many of the advanced countries. So if you are able to do everything in 1 week, they are very happy. They are willing to spend more money to reduce the disruption to traffic. So those are the some of the situations where you can propose FRP. But in any new product, you must do full-scale structural tests. That's another thing which is difficult in India, in the sense, except for a few major institutions like IIT Madras and all, and Structural Engineering Research Institute in Madras, places like that, you really don't have very large testing facilities. And testing this kind of stuff is very expensive. So that's something you have to consider. Before you use them in practice, you really have to test these members at full scale. Full scale, that's most important. Small scale is fine, but full scale is something that will really cover your liability. Like as a design engineer, you are signing the document, that's your design. So that's your liability, right? So to cover your liability, you have to somehow do some load testing. So that's a little bit harder in India, but it can be done. So in US context, they do this kind of load test. My students have done this kind of tests. Of course, they don't actually drive the truck, but they will order the truck, they'll take the weights of the loads, everything. And then they will do the instrumentation. Our students have done that, my students. And they will have instrumentation, they will measure the strains, measure the crack widths, measure the vibration characteristics, all kinds of this type of testing. We have done this kind of tests. This is not my test, by the way. This is someone else's test. And of course, there are new types of, not new anymore. 15, 20 years back it was new, but not new anymore. This is a honeycomb construction or honeycomb structure. So I have a sample of this also. So they place one plate on the top, one plate at the bottom, and you have this honeycomb so-called formation. And then you fill it with foam, structural foam though, not normal foam, structural foam. So the foam and the ribs will take the shear loading, and the top plate and the bottom plate will take the flexural loading. So they use this in some of the aircraft structures, so as the floor panels. So, and it's so light, you can see it's very, very light. So with that, I have some exhibits here. After we finish our session, you can come and take a look. I will just move on to the next item because we are a little bit behind already, which is not good, but that's okay. Let me see. It's a very long presentation. But anyway, we'll go through some of this at least today, if you don't mind. Is that okay? So that's a big difference between our Indian audience and American audience. If I say, is that okay? No, we'll do it tomorrow. So I had to go. I had to go to gym. Okay? How can you not go to gym? That's more important than this, right? So it's really funny. They will not agree. No, we have to go. Let's end now. Okay, fine. Go. So now I'll introduce you to numbers. Just if you'll get a feel for numbers. So let's do that. I'll go a little bit faster if that's okay. It's all written up. So if you read it quickly, you'll learn most of it. Okay, so we have ACI definition where we said at least our aspect ratio is at least 100. That's what we said. Okay. Now, we already know how we use continuous fibers. There's some repetition here, so we don't want to go through in details. Continuous fiber is very useful, very important. We need that. But sometimes they also use chopped fibers that are not necessarily continuous. So you add a 10% or 20% a larger fiber volume, and that will take care of the strength aspects. And then make sure you have good distribution and microstructural characteristics. So the composite strength is dependent on fiber mechanical properties. Very, very important. In the direction of the fiber, you'll have very good strength. In the perpendicular direction, that is direction transverse to the fiber, you will not have very good strength. Length, shape, composition of all these fibers will make a difference. Mechanical properties of resin matrix will make a difference, but not as much as the fiber. We'll do that tomorrow when I will explain to you how, say, 50% by volume fraction, how much is the strength going to be for the composite. If it is 25%, what is it going to be? If it is 10%, what's it going to be? Very simple mechanics. It's nothing complicated, but we'll talk about it tomorrow. And then we have, we need to have better bond or good bond between fiber and matrix. Okay, so why do we need polymer matrix? We already mentioned it. I mentioned this previously, but primarily load transfer and protection of fibers. I mentioned that. In case of interlaminar shear, what is interlaminar shear? You have a composite, let's say this is a composite plate, it has millions of fibers in the cross section, right? So if I apply a load, this will, the layers of the composite would want to slide on each other, right? So that property is mainly dominated by matrix, not the fiber. Are you with me? Whereas the tensile strength in the direction of the fiber is dominated by the fiber. Interlaminar shear, in-plane shear, those are all dominated by matrix properties. Transverse stiffness and strength, even strength is dependent on matrix properties. We'll talk about this and we'll attach some numbers. We'll get a feel for numbers tomorrow. Stability of fibers in compression is completely dictated by polymer matrix because fibers have very, very large aspect ratios. Therefore, they cannot carry any compressive load. So if they are completely surrounded by matrix, the buckling or micro buckling of fibers is prevented. And of course, operating temperature depends, operating temperature of the composite depends on the glass transition temperature. That's what it's known as, glass transition temperature of matrix. We'll talk about it in a minute. Okay, this is where we have a very important concept to be remembered. There are different types of matrices. One is thermoset matrix and the other one is thermoplastic matrix. The first one is actually normally it's a two-part system. Then once you mix the two parts, the chemical reaction will start. And once the chemical reaction starts, it's irreversible. That means you cannot stop it. So whatever shape you gain or you create before the chemical reaction will remain after the chemical reaction. You cannot change it. Big problem, right? That's what we were talking about this morning, or about for reinforcing bars. If you have ties, you have to make those ties in that shape. You cannot make a straight bar and then bend it. It's not possible at all. It will just break. It will brittle. So it will break. So thermoset matrix has that limitation. Once the chemical reaction starts, you cannot stop it. Whereas thermoplastic material, which is more common in aerospace applications, I have one thermoplastic material panel here. If you are interested, take a look. This is for a real Boeing aircraft. And this is the panel which is attached to the floor beams. So this is a real panel. You'll see this is a composite. And I'm doing some work with these guys. They're giving me some, or they're going to give me some money to do some testing on the composite panels. So that one is a thermoplastic matrix composite. In that case, you can actually heat the part, and when you heat the composite, it becomes softer. And then you can bend it, you can do whatever you want, and then when you cool it, it becomes hard. So that's the advantage. You can do it multiple times. You can actually heat it, change the shape or form, and then cool it, and it remains in that shape. So that's the advantage of thermoplastic matrix. But this is very, very expensive. Therefore, in civil engineering, again, coming back to our applications, civil engineering applications are all cost-sensitive structures or applications. Therefore, we use mostly we use thermoset matrix, which means we cannot bend the bars after they're fully formed. Okay? Now, I mentioned all of this. Most common in structural applications, high processing speeds. These thermoset matrix resins have a part life. That means you can only work with those. You can only work with those before the expiration date. And once you mix it, you have only a certain time before which you can make the composite. Just like in normal concrete, once you start mixing cement and water, you cannot wait forever to place it in forms, right? It's just like that. Okay. So curing time again depends on what you are using. It can be accelerated curing method. It can be reduced or prolonged curing method. You can apply heat to accelerate the curing process. So there are everything you do with your curing is dependent on the chemistry of the product. So you should never hesitate to ask questions to the supplier. You say, what should I do? They should have an answer. Okay? So for everything, you should consult your supplier, make sure you use the right process, right temperature. Everything is important in everything actually. Even in reinforced concrete construction, we have to make sure everything is done to the specifications. Okay, so there are different types of thermoset matrices. Most of them are polymers. They are polymers. So unsaturated polyester, vinyl ester. This is probably the most common one. It says about 85%. Vinyl ester is more expensive, but the basalt bars I have here and more expensive bars, they are made with vinyl ester. There are two-part epoxies. These are not necessarily common, but for bars at least. And then phenolics. So there is another process called pre-preg. So what they do is they do half of the process, mixing process, completed and partially completed, and then later on they complete the full process. So I don't know, here do we have, I'm not sure, do you have packed concrete in stores? Can you go and buy them? I don't know. I don't think so, because you can do actual concrete anyway very easily. So, I'm sorry. Somebody was saying something? So in US and many of the other countries, if you're everything, it's so expensive, so you cannot engage a professional engineer or somebody to do small work at your home. So you do it yourself. Everything you do yourself. Okay. So there is packed concrete, dry mixed in a sack, comes in 20 pounds, 30 pounds, 40 pounds pack. You bring it home or wherever you are doing your work, mix some water, and it's like concrete. So that's like pre-preg. Okay. So all these composite industries, they are able to do that. They'll give you prepared mix, they'll give it to you, they'll give you the chemicals, they'll tell you what to do, and you can make a composite, maybe boat or something like that. Maybe boat is a little bit too much of a stretch, but kids like 8-year-olds, 10-year-olds, they play with composites, they make stuff. That's the very common thing in US. Okay, so I already mentioned this. Each one has its own advantages and disadvantages. Unsaturated polyester, the UP, they have better thermal insulation than most construction materials. Vinyl ester is high strength, but it's also more expensive. So epoxy resins are high performance resins, corrosion resistant. So they have different types of or different advantages and disadvantages. What I would do is, if I am designing a brand new product, which is very unlikely, most of us will not design any new product, or at least that's what I think. We will use some product, but we may not design an absolutely new composite product. So if you are using someone else's product, you must ask questions. and then make sure you understand what needs to be done. So here we have, I'm sorry, I'll just go back 1 minute, okay, if you don't mind.